We'll start by taking a look at ordered pairs. An ordered pair consists of two components written inside a pair of parentheses and separated by a comma. The first element is naturally called the first coordinate, and the second element is called the second coordinate. Ordered pairs are usually formed in a contextual manner so that there's some well-defined relationship between the first coordinate and the second coordinate. For example, suppose you sell hot dogs for $2 each. Then we can form a table describing the situation as follows. In this left column, we'll put in the number of hot dogs. In the right one, we'll put the total price. So for example, one hot dog will correspond to 2 times 1, which is $2 for the price. 2 hot dogs will be 2 times 2 or $4. 3 hot dogs, 2 times 3 or $6. Now, in mathematics, we usually like to generalize the situation and say, okay, so how much will n hot dogs cost for some unknown number n? Then we know that all we need to do is multiply that number by 2 to get the dollar amount. Now we can represent this information as a set of ordered pairs. So here we would have a set containing these ordered pairs, where 1 is matched up with the price $2, 2 is matched up with the price $4, 3 with $6, etc., and n with 2n dollars. Yet another way to represent the data is using functional notation. For example, we can think of this purchasing machine and say when 1 goes into it, 2 comes out, 2 goes into it, 4 comes out, etc. So we'll get to talk more about functions later. We graphically depict ordered pairs using the Cartesian coordinate system, named after the great French mathematician René Descartes. The Cartesian coordinate system is composed of two perpendicular real number lines, like so, intersecting each other at their 0 points, okay? And creating a point of intersection right there, which is known as the origin, which is the ordered pair 0, 0, basically. The name that we usually reserve for a horizontal line is the x-axis. Each of these two horizontal line or number lines are called axes. The horizontal line we refer to as the x-axis, the vertical one as the y-axis. Of course, if we're dealing with a different context, we can always use different letters for these. There's nothing about those letters that's set in stone. Oftentimes in physics, for example, they'll use T for the horizontal axis. In finance, they use other letters. So there's no attachment that should be formed to these letters, okay, per se. However, once we do start learning about functions, it is a general practice that we plot the inputs using the horizontal axes and the outputs using the vertical axes. Now, these two axes, notice, break up the plane into 4 different parts, right? The first part is the first quadrant. Each of them is called a quadrant. And notice that if you pick a point in this quadrant, both the x and the y coordinates will be positive, right? Because here we start at 0 and positive numbers are to the right. Here and the negative numbers are to the left. On the y-axis, we start at 0 and then the positive y values go upward and the negative ones go downward. So in quadrant 1, both the x and y coordinates would be positive. Now we move counterclockwise to get to quadrant 2, where the x coordinate would be negative and the y coordinate would be positive. Continuing in a counterclockwise fashion, we reach quadrant 3, where both the x and y coordinates of a given point in this quadrant would be negative. And finally, moving on in a counterclockwise fashion, we'll get to quadrant 4, where the x and y coordinates of a typical point in this quadrant would be positive and negative respectively, right? The x value would be positive, the y value would be negative. If a point lies on the axes themselves, then it's called a quadrantal point, okay? And a quadrantal point does not belong to any quadrant, okay? The whole point is that it lives on one of the two axes that create the quadrants, so it does not belong to any of the quadrants. Here is an example of some points in the Cartesian coordinate plane. When you see an ordered pair like 2, 3, you can think of it as a pair of instructions, right? It says start here at the origin 0, 0, go this many units in the horizontal direction. Depending on the sign, you either go right or left. So here it's a positive 2, so we move 2 units to the right, and the y value coordinate is positive as well, so we move 3 units up and we reach this point, okay? So 0, 0 itself, it means start at the origin, don't move to the left, and don't move up or down, right? Don't move left or right, and don't move up or down. So where would you end up? Right there at the origin, right? So here for this one, we're going to go 3 units left and 1 unit up. For this point, we're going to go 1.5 units to the left and 2.5 units down. All right, in order to establish some of the results that we would like to establish, we need to remember the Pythagorean theorem, which is, of course, the famous theorem about right triangles, where the sum of the squares of the two legs is equal to the square of the hypotenuse. Now, please do not get attached to the letters A, B, and C here and think that it's always going to be the case with a right triangle where a squared plus b squared equals c squared. No, it just happens to be so because a and b are representing the legs and c is representing the hypotenuse. If that were not the case, you wouldn't get the same result. Consider this, for example. Notice in this triangle here that you have A is the hypotenuse and B and C are the two legs. So the correct relationship here is B squared plus C squared equals A squared. So the important thing to understand is the relationship between the three sides rather than just the formula A squared plus B squared equals C squared. In fact, I oftentimes like my students to remember that it in this way, that leg 1 squared plus leg 2 squared equals hypotenuse squared. You'll be less likely to get yourself in trouble if you remember it that way. It's much safer. Here's a very quick and very important application of the Pythagorean theorem, and it results in what we call the distance formula. It helps us find the distance between any 2 points in a plane. And notice that if you have any 2 points in a plane, you can form a natural right triangle from them in this manner, right? Now, the important thing to understand is what these lengths will be, because look, if this is the point x1, y1, right? We're missing a little parentheses here. I'll just add that. So if we're dealing with the point x1, y1 here, right, that means the x coordinate here is x1 and the y coordinate here is y1, right? So together they form the point x1, y1, right? Now, for this other point, since the x coordinate is x2, that means this point here is x2 and the y coordinate is y2, so that means this y value here is y2. So that makes this distance right here y2 minus y1, right? Larger number minus smaller number, and it makes this distance here x2 minus x1, right? Now, if this distance is the one that we're interested in, the distance between the points P1 and P2, then that distance is going to just be the square of that distance is going to be the sum of the squares of these two legs, right? So quantity x2 minus x1 squared plus quantity y2 minus y1 squared. So since we're interested in the distance itself, we're going to take the square root of both sides, and or rather we're going to apply the square root property. That's a better way of thinking about it, because if d squared is this expression, that means d is going to be plus or minus the square root of this the same expression by the square root property. But remember, distance is always non-negative, so therefore we only take the positive case to be valid. So we get the square root of quantity x2 minus x1 squared plus y2 minus y1 squared, and this result is called the distance formula because clearly it gives us the distance between any 2 points in the plane. Let's go ahead and apply the distance formula to find the distance between these 2 points. Notice that here we can think of this point as x1, y1, and this point as x2, y2, right? So we know that the distance is given by the square root of x2 minus x1, quantity x2 minus x1 squared plus quantity y2 minus y1 squared. And the reason we make a big deal out of saying quantity, for instance, is the fact that if I just say to you x2 minus x1 squared, that's what it's going to look like. The only thing that's going to get squared is the x1. If I want to make sure that you're squaring the entire expression x2 minus x1, that's when you would say quantity. So the moment you say quantity, a parenthesis is opened. The moment you mention an operation such as squared, that's where the parenthesis is going to get closed and the operation is going to take place. All right, so we get equals. Now x2 is 5 and x1 is 2. So quantity 5 minus 2 squared plus, now y2 is 7/2 and y1 is -1/2. So be careful, you need that negative sign like that. It's whatever y2 is minus whatever y1 is. If it happens to be negative, then that's so be it, right? All right, so now we have the square root of 3 squared, right? 5 minus 2 is 3. And this becomes 7/2. Negative times negative is positive, so it's 7/2 plus 1/2. So that's 8/2, which is of course 4. So we get the square root of 3 squared plus 4 squared. Now you may recognize that. That's a famous, what's called a famous Pythagorean triple, because that gives you the square root of 9 plus 16, which is the square root of 25, which is 5. Now, three numbers that happen, in other words, 3 squared plus, now we're done with the problem, by the way. That's the distance, right? Now, but just as a side note, if you have three numbers that satisfy the Pythagorean equation, like this, okay? They're called, those three numbers are called the Pythagorean triple, okay? Now, that's not the only Pythagorean triple that exists. There are infinitely many, right? But that just happens to be the most famous one. A couple of other famous Pythagorean triples are 5, 12, 13. In other words, 5 squared plus 12 squared equals 13 squared. 7, 24, 25. 7 squared plus 24 squared equals 25 squared. Make sure you verify that on a calculator just to convince yourself. And the nice thing is, so we usually put them in the form of ordered triples. So we have 3, 4, 5. We have 5, 12, 13, right? 7, 24, 25. Now, the fact of the matter is that any multiple of a Pythagorean triple is also a Pythagorean triple. Like, for example, if I multiply this by 2, meaning each member of it by 2, right, we end up with the 6, 8, 10 Pythagorean triple. This one will give us, multiplied by 2, will give us the 10, 24, 26 Pythagorean triple. This one would give us the what? 14, 48, 50 Pythagorean triple. Now, particularly the multiples of this are pretty well known. The first one, the 3, 4, 5. Like, for example, if I were to multiply it by 3, I would get what? 9, 12, 15. So there's another one. Or by 4, etc. So just a side note, but an interesting one. It's good to be familiar with these Pythagorean triples as we run into them. Okay, here we have a problem that relies on the fact that the Pythagorean theorem is a biconditional, meaning that if you have a right triangle with legs AB and hypotenuse C, then A squared plus B squared equals C squared, and vice versa. If you have a triangle in which A squared plus B squared equals C squared holds, then it's a right triangle. So in this problem, we're going to measure the lengths of these three sides. Now, this graphic may not be given to you. I just put it here for reference, and we're going to show hopefully that the squares, sum of the squares of two of the sides equals the square of the third side, in which case we've established that it's a right triangle. So we're going to measure the length AB first using the distance formula. Now, if you recall from geometry, if I just write AB without a bar on the top, that does indicate the length of segment AB. So we don't need to write the distance between A and B. We can just write AB, and that means the length of this segment, which is of course the distance between A and B. So we get the square root of, now in this case you can let either pair be x1, y1 and the other one be x2, y2. We'll just let this one be x2, y2. So x2 minus x1 squared, so 12 minus negative 2 squared plus y2 minus y1 squared, so 3 minus 5 squared, and we end up with the square root of, now this 12 minus negative 2 becomes 12 plus 2, so it's 14, so 14 squared plus 3 minus 5, that's negative 2, so quantity negative 2 squared. All right, so we'll go ahead and get some help from a calculator to see what that is. So we have 14 squared plus basically 4, right? And we get 200. So that's the square root of 200. We can leave that as is for the time being. Now we're going to find this length, BC. So that's going to be the square root of x2 minus x1, so 10 minus 12 quantity, 10 minus 12 squared plus y2 minus y1, so negative 11 minus 3 quantity, negative 11 minus 3 squared, which is equal to the square root of quantity negative 2 squared plus quantity negative 14 squared. Now, of course, we know that quantity negative 14 squared is going to have the same value as 14 squared in the previous part, and this quantity negative 2 squared is of course the same as that quantity negative 2 squared, so therefore we know this is going to end up being the same sum, so we don't need to calculate it again. So that's also the square root of 200. So now we'll calculate AC, which is going to be the square root of x2 minus x1, so 10 minus negative 2 quantity 10 minus negative 2 squared plus quantity negative 11 minus 5 squared. So we have the square root of 10 minus negative 2 becomes 12 squared plus this one is quantity negative 16 squared. So now we'll calculate that. So we have 12 squared, and of course I can just put in 16 squared because it makes no difference. The square of negative 16 is the same as the square of 16, and we get 400. Now, of course, we want to prove that the square of the one side plus the square of another side equals the square of the third side. So we're going to look at the squares. So the square of AB plus the square of BC, those are the shorter sides, so we assume those would be the legs. We want to know if that's equal to the square of AC. And of course, the square of AB is just going to be 200, because what happens when you square the square root of 200? You get 200. And the same goes for the square of BC. And the square of AC is 400. So if this equation is true, we're in good shape. Indeed, we have 400 equals 400. Therefore, the Pythagorean equation holds, and therefore the answer is yes, they do. They do, in fact, form the vertices of a right triangle. All right, so there's a quick application of the distance formula. Make sure you can handle a simple problem like that. Now, do notice we could have just looked at the square of each of these from the beginning and not have to deal with square roots at all, but I wanted you to go ahead and see the distance formula in action, so with the square roots and all, so it doesn't hurt to go through the extra step. All right, next we want to look at the concept of collinear points. Three distinct, which basically just means different points, are said to be collinear if there exists a single line that contains all three of those points. Now, 3 points will be collinear if the sum of the distances between two pairs of points is equal to the distance between the remaining pair of points. The basic idea here is to find the distance between each pair of points. So if you take a look at, say, these 3 points here, A, B, and C, basically, for example, here, if we can show that AB, which is the length of segment AB plus BC, is equal to AC, we've established that in fact this is a straight line segment, because then we're getting the shortest distance between A and C. So the idea is to find the distances between all pairs of points that are possible, these 2 points, these 2 points, and then these 2 points, and show that the sum of 2 of them add up to the third distance, and we've established that they're collinear points. All right, so here's the direct application. We're going to try to determine whether these points are collinear or not. And you should be able to handle this. So go ahead and try it. It'll be a good exercise for you. All right, so we'll go ahead and find all three distances basically between these points. So let's start with AB. That's these 2 points. So we know that we have the square root of 2 minus -1. So quantity 2 minus -1 squared. That's x2 minus x1 squared. Plus quantity y2 minus y1 squared. So -4 minus 5 squared. And that gives us 2 minus -1 becomes 2 plus 1, so 3 squared, plus -4 minus 5, that's -9. So we want the square of -9. So that's the square root of 9 plus 81, which is the square root of 90. Okay, so now we'll go ahead and find BC, which is the length of segment BC. So that's going to be quantity 4 minus 2 squared plus quantity -10 minus -4 squared, which ends up being the square root of 2 squared, plus -10 minus -4 because it becomes -10 plus 4, so that's -6. So we want the square of -6. So that's going to be the square root of 4 plus 36, which is the square root of 40. Now keep in mind, we're not going to be dealing with squares of distances here, so we do need to keep the square roots for sure here. It's not an option to just look at the squares here. Finally, we'll go ahead and look at AC. So we're finding the distance between these 2 points, which is the square root of quantity 4 minus -1 squared plus quantity -10 minus -4 squared, which gives us the square root of, now that's going to become 5 squared plus this here is -10 plus 4 once again, right? Oh, I can see I made a quick mistake here. That's not -4, right? What should it be? We're looking at AC, so 4 minus -1 and then -10 minus 5. So my bad there, let's fix it. So it's -5 squared. So basically that's the square of -15. All right, so we get the square root of 25 plus, let's see what 15 squared is. $225. Which ends up being the square root of 250. All right, so these are clearly the smaller segments, so the sum of these two should be this value if we're going to be on on the right track. So we want to know if the square root of 90 plus the square root of 40 is equal to the square root of 250. Now, we could verify these in different ways, but these are kind of nice numbers in the sense that they can be quickly simplified. Notice this one is the square root of 9 times the square root of 10, and the second one is the square root of 4 times the square root of 10. And on the right side, we have the square root of 25 times the square root of 10. So we have 3 square root of 10 plus 2 square root of 10, and we want to know if that's equal to 5 square root of 10. And of course, 3 square root of 10 plus 2 square root of 10, those are like terms, we can combine them. That's just 5 square root of 10, which is equal to 5 square root of 10. So it checks out. Indeed, we have shown that AB plus BC is equal to AC. Therefore, we have established that the 3 points are indeed collinear. All right, so there's a nice quick application of the distance formula once again. Okay, so very simple, but an important problem in helping you understand how to apply some of these concepts. So make sure you can handle it, and we'll proceed. One of the other things that we run into having to find from time to time is the midpoint of a given segment. And the coordinates of the midpoint of a segment with endpoints at the point A with coordinates x1, y1, and B with coordinates x1, x2, y2 is given by this formula. It's basically, you know, you find the average of the x values and then the average of the y values, and that gives you the midpoint. Definitely one of those formulas that you will want to have in your bag of formulas. Now, of course, if these points are on the number line, it's very easy and quick to find the midpoints. But as far as a midpoint is concerned, they're not that much more difficult if they're not lying on the number line either. So we'll just apply the formula. You will know that it's a good idea to always write your formula down first. We didn't do so for the distance formula because there's so much writing. I'm trying to save time on the video, but it's a good idea to do it. So we know that the midpoint is going to be x1 plus x2 over 2, comma, y1 plus y2 over 2. So here we can think of this as x1, y1, and think of this one as x2, y2. And we're going to get 8 plus negative 6 over 2, comma, negative 4 plus 1 over 2. So now 8 plus negative 6, that's 8 minus 6, so it's 2. So we have 2 over 2, comma, and this is going to be negative 3 over 2. So the simplest form will be the ordered pair 1, negative 3 halves. And that is the midpoint of those 2 points in the Cartesian coordinate plane. All right, so very simple, finding a midpoint. Okay, so here's a problem with a little bit of a twist here. They're giving you 2 points, A and B. Like, we can just do a quick sketch. So we have A at negative 6, 12, and somewhere to the right here, because 8 is of course to the right of negative 6, and then a little bit, quite a bit below, we have like the midpoint. And what they want is the coordinates of B, which is some point x2, y2. So we have the 1 point and we have the midpoint, and we want to find the other point. Okay, so we know that x1 plus x2 over 2 comma y1 plus y2 over 2 should equal to the ordered pair 8, -2, right? Now, we do know what x1 is and what y1 is. Think of this as x1, y1, right? So this means x1 plus x2 over 2 equals 8, and y1 plus y2 over 2 equals -2, right? Now we'll plug in what x1 is, which is -6. So we get -6 plus x2 over 2 equals 8. And for this other one, we'll substitute y1, which is 12, plus y2 over 2 equals -2. If we throw a 1 under the 8 and the -2, we can cross multiply. So we get -6 plus x2 equals 16. So x2 is equal to 16 plus 6, right? Move the -6 to the other side, so we get x2 is equal to 22. Now we do the same on this other side, and we get 12 plus y2 equals -4. So y2 equals -4 minus 12. So y2 equals -16. There we have it. We just found the coordinates of the point B, and they happen to be 22 and -16. All right, so as a good exercise, what you could do is you could go ahead and find the midpoint of these 2 points and verify that it is this. That would be a good check to make sure that you've done it correctly. So take a couple of minutes to do that and then move on to the next problem. Okay, here we'll look at a simple modeling application of the midpoint formula. The following figure depicts how a graph might indicate the increase in the sales generated by fast food restaurants in the United States from 167.7 billion in 2011 to 233.7 billion in 2017. We're going to use the midpoint formula and the 2 given points here to estimate the sales from fast food restaurants in 2014 and compare it to the actual figure of 195.4 billion. So we're, again, word problems can sometimes sound scary, but when you listen to what they actually want, it's usually pretty simple. So here we're finding the midpoint of these 2 points. Remember, you need ordered pairs. So the points are 2011, comma 167.7 and 2017, comma 233.7. Okay, so applying the midpoint formula, which again, it's helpful to write it down before you just plug in. So we get x1 plus x2 over 2, comma y1 plus y2 over 2. Here we'll let this be x1, y1, and this be x2, y2. So we end up with 2011 plus 2017 over 2, comma 167.7 plus 233.7 over 2. All right, so seeking the help of our trustable friend, we get, well, we know this is going to be 2014, right? 11 and 17 is 28. And when you divide that by 2, you get 14. But just to be on the safe side, we'll try it. All right. Just as we thought. And then we'll do 166.7 plus 233.7 and divide that by 2, and we get 200.2. So according to our model, which is this straight line estimate of what the growth should be, it should be that much, which is actually higher than what? Than the actual numbers reported. So a model is a good estimate, but it's never, of course, going to be as good as having actual data, correct? So that's what we're establishing here. All right, so there we go. All right, and the last thing we want to handle in this video is doing some simple graphing, but first by finding some solutions that we can graph. So in the first stage, we're just going to find some ordered pairs that satisfy each of these equations. So that's a very simple process. Of course, we just need a table with x and y in it, and we're going to substitute for one and get the value for the other by plugging in. Now we'll see which one is the better choice in each case. So in this case, we notice that y is given in terms of x. So it's much easier if we substitute values for x and then find the corresponding values for y. So now which ones we use for x make no difference at all. So you can pick your favorite numbers, or just go with the simplest ones that come to your mind. For example, 0, 1, and 2. So when you plug in 0 for x, you get 4 times 0, which is 0 minus 1, gives us negative 1. When you plug in 1, you get 4 times 1, which is 4 minus 1, which gives us 3. And when you plug in 2, you get 4 times 2 is 8 minus 1, which is 7. So since they wanted us to give our answers in the form of an ordered pair, we're going to say 0, negative 1, 1, 3, and 2, 7. Ordered pairs, by their very name, indicate that order matters, right? So the agreement is we're always going to write x first and then y, okay? So how about this next one? Which one do you think is better to plug in for first, right? In this case, x is given in terms of y, so it's easier if we give y values and then solve for x, right? Now here you got to be careful, because you can't just plug in any number you want. 0 would not be a good choice, because 0 minus 1 is negative 1, and the square root of negative 1 is not a real number. So in fact, you know what the domain is, because you're going to want y minus 1 to be greater than or equal to 0, which indicates y has to be greater than or equal to 1, right? In this case, we're really looking at y values, so it's kind of a range issue, but given that x is given in terms of y, you can think of it in the reverse direction. Okay, so now notice that the smallest value for y that I can substitute is 1. So I'll go ahead and start with that. And then I can do 2. So 1 gives me square root of 1 minus 1, which is square root of 0, which is 0. 2, I get 2 minus 1, which is 1. The square root of 1 is 1. Now, if I go 3, I end up with the square root of 2. Or if I really want just nice whole numbers to plot a graph, then what I could do is go to the next number that's going to give me a perfect square, right? So I want y minus 1 to be 4, for example, so that when I take the square root, I get 2, right? So I just say y minus 1 equals 4, solve that quickly, so I get y equals 5. So I know if I substitute 5, I get 5 minus 1, which is 4. The square root of 4 is 2. So this way I can avoid less desirable numbers if I'm trying to plot points, for example. All right, so the ordered pairs here would be 0, 1, 1, 2, and 2, 5. Again, you may come up with different ordered pairs that are solutions, and that would be totally fine. But notice we still gave the solutions using x first and then y, right? Even though we plugged in for y first, that doesn't matter. In the end, you're going to write your ordered pairs in the correct order. Okay, how about this next one? All right, so y is given in terms of x, right? So again, it's easier if we plug in some x values and get some corresponding y values. So why don't we do a couple of negative values just for fun? Okay, what if I plug in -2 for x? Well, the square of -2 is 4 minus 4 gives me what? 0. Now the square of -1 is 1 minus 4 will give me -3. The square of 0 is of course 0 minus 4 will give us -4. Okay, so just like that. So the ordered pairs of interest are 2, 0, -1, -3, and 0, -4. All right, so that's how we handle that one. Okay, so here we're going to take it one more step and actually graph it. Now, this is a linear equation, and we know there's an important property that helps us graph linear equations, and the fact is that 2 points in a plane determine a line. Okay, so in actuality, all we need is to plot 2 points. Now, oftentimes we do 3 points just to make sure we didn't make any kind of mistake. But if you are very careful, you can really get away by just plugging in and finding 2 points. So why don't we do that? So if x is 0, now given that y is given in terms of x, I'm going to give x a couple of values and find the corresponding y values. When x is 0 and when x is 1. When x is 0, I get 4 times 0, which is 0 minus 1 is -1. When I plug in 1, I get 4 times 1, which is 4 minus 1, which is 3. Now all I need to do is graph those 2 points. So ordered pair 0, -1 is right here. And 1, 3, I would go 1 to the right, and then 1, 2, 3 up. Then all I just need to do is draw the line that goes through those 2 points. And there we have it. We know it's a straight line. Of course, mine doesn't look very straight, right? But it is. Just believe it. All right, and that's how we do that one. All right, so this should look familiar to you because these are the ones we found ordered pairs for, right? So if you recall, here it's better if we give y values first and then get the x values. So, and remember, we have to start with y equals 1 because we want y minus 1 to be greater than or equal to 0. So y has to be greater than or equal to 1. So 1 will give us the square root of 1 minus 1, which is the square root of 0, which is 0. 2, if you recall, gave us 1. 2 minus 1 is 1. Square root of 1 is 1. And then remember, we jump to 5 to get a nice whole number for x. And 5 minus 1 is 4. The square root of 4 is 2. So now we go ahead and we plot those points. So 0, 1. You want to make sure, even though technology is so readily available, you want to make sure you don't lose the ability to do some basic plots on your own, just by hand, as I'm doing here. So 1, 2 is the next one. So 1 and 2, and then 2, 5. So 2, 1, 2, 3, 4, 5. All right. So this is gonna look something like that. All right. Here, let's make it, force it fit. All right, so it'll be nice and smooth. There will be no jagged edges. So let me try it one more time. All right, it's very difficult to do on a screen, I must admit. It's much easier if I were doing this on an actual whiteboard, but anyway, there it is. You get the idea. Here, we can take a better look at it together on an graphing app, such as, for example, Desmos. Let's go do that. All right, so here we want to graph x equals square root of y minus 1. All right, so I didn't do too badly, but this of course looks much nicer. All right, then here's one more for the road. Okay, so here we're going to go ahead and plug in some values. Now we're going to become pretty much masters of these kinds of graphs. These are quadratics, but for the time being we're just doing some very elementary work. Now here we are going to want to plot some negative as well as positive ones because of this squaring effect. This is going to have symmetry, so it's good to have some numbers from both sides of the line of symmetry. So we'll do -2, -1, 0, 1, 2. So when I plug in -2, I get the square of -2 is 4 minus 4 is 0. -1 gives me the square of -1 is 1 minus 4 is -3. 0 squared is 0 minus 4 gives me -4. 1 squared is 1 minus 4 is -3. And 2 squared is 4 minus 4 is 0. Here it's really nice to see the symmetry, as you can see right there. You can see this is going to be an important point. This is indeed the lowest point of this upward facing parabola. It's called the vertex. Again, we're going to learn quite a bit about these later. So -2, 0, -1, -3, 0, -4, 1, -3, and 2, 0. So very beautifully symmetric. Sometimes with these it's a little easier if you do the little cup here and then just extend it like that, and then just extend it on both sides. All right, so there's a rough sketch of this shape, which is called a parabola, and that's how you go about doing this. All right, so that should wrap it for this basic lesson. It's one of our easiest lessons, probably all term long. Go ahead and practice some, and take care until we see you again next time.